So for the second talk today, we'll have Ningchuan Zhang to tell us about exotic KH local Picard groups and the vanishing conjecture.
Thank you very much for the invitation. Thank you very much for the invitation. So today in this talk, I'm going to describe a joint work in progress with the first speaker of today, Dominic Cover, on exotic KH local Picard groups under the assumption that the prime and height satisfy 2h minus 1 equals h squared and its relation with the vanishing conjecture. So the background of this project is, the background. So the talk will have three parts. In the first part, we will review the algebraic aspect of KH local Picard groups. The second part will use duality to relate the Picard group computation, exotic Picard group computation, to a certain group cohomology, and eventually to Greek letter elements. That will be the last part of my talk. So the background of this talk is back in the first, I think the study of Picard groups in chromatic homotopy theory was initiated by the paper of Hopkins, Mahovot, and Sadovsky, where they show that the exotic KH local Picard group vanishes when the prime and height satisfies pH minus 1 does not divide the height, and 2p minus 1 is greater than h squared. So in our project, we'll study the next case, that is when 2p minus 1 is equal to h squared. So two observations. First, this assumption automatically implies pH minus 1 does not divide h, so that's automatically satisfied. And second is actually it's unknown where there are infinitely many such pairs of primes and heights. And of course, our project, we do not seek to answer this question if there are infinitely many primes. This is still an open question in number theory. But nevertheless, using SIG, we can produce millions of such pairs. So who knows? Yeah, so our main results are the following.
Ningchuan, yes? Question about the number theory. Is that a question that's actually like known to number theorists, or is it like unknown because just nobody ever asked it just because it was some like random collection of conditions, or?
I think it's known to, it's open question in number theory. And
it's the conjecture of Euler.
Oh, okay. All right, great. So it's an established.
It's a general question about irreducible quadratic, like primes showing up as solution, showing up in irreducible quadratics.
Okay. Thanks.
Yeah. So our main results are suppose the prime and height satisfy this assumption. So our main results now current status has three parts. So first, when the Smith-Toda complex way of h minus 2 exists, then elements in kappa h cannot be detected by this Smith-Toda complex. So that means if we smash this exotic element with h minus 2, we get KH local which way of h minus 2. And when the Smith-Toda complex is known to exist, say at height when this, e.g. this is true when the height is 3 and prime is 5, and height is 5 and prime is 13. So that is at p equals 5, we know way of 1 exists. And when p is equal to 13, we know way of 3 exists. The second part is if a certain conjecture, if a version of the vanishing conjecture, which we call the reduced homological vanishing conjecture, holds at prime 5 and height 3, then kappa 3 is indeed 0 when p is equal to 5. And more generally, there are some bounds, some common bounds on the divisibility of Greek letter elements at height h that would imply both this vanishing conjecture and kappa h is equal to 0 when 2p minus 1 is equal to h squared. And actually, I guess I should tell you what is this conjecture, a statement of this conjecture. So this is a special case of a conjecture by Mac Hopkins, and we call it a reduced homological vanishing conjecture, which says it's homological since it's the group zeroth group homology. So it says the inclusion of the finite field of size p to the h to the Lubin-Tate group, Lubin-Tate space mod p, and this inclusion induces an isomorphism in the zeroth group homology. Okay, so what's the strategy? What's the strategy? The strategy has many steps. The first step is to use a map defined by Gross, Ham, Mahovan, and Rask, where they define algebraic detection map from the case the exotic Picard group at height h to this group cohomology in cohomology with 2p minus 1 and the coefficient in pi 2p minus 2. And this map we can show it's injective under our assumption. So in order to show, say, kappa H is 0, it suffices to say, to compute this group cohomology. And now, since under our assumption, this is really the top degree group cohomology. This is the top degree group cohomology, and the assumption also implies SH, the smaller molar stabilizer group, has a cohomology equality H square. So in that case, we can show that for this molar module, pi 2p minus 2 of EH, the top degree cohomology, there's an isomorphism with more p. And then we can use Poincaré duality to relate top degree cohomology to both the 0th degree homology and 0th degree cohomology. For the 0th degree homology, it's just the real Poincaré duality. But for the cohomology version, then there's we need to take Poincaré dual. We need to take Poincaré dual. And then the next thing is now we need to identify. So we'll try to relate our computation Greek letters. So we'll use the cohomological version of Poincaré duality. To do that, we need to identify the equivalent Poincaré dual of this molar module. And this dual, the formula, if you know the formula for Gross-Hopkins duality, this formula will involve the determinant twist of the stabilized group action. So but in our case, we know we can take the dual and then molar by p. And in the paper by Gross and Hopkins, they said that they identify this determinant twist more p as a limit of finite suspensions. And then using a change of range theorem, we can translate this computation to BP computations. And once at that step, then it's Greek letter computations. So that's for the exotic Picard group, and we can basically do the same thing to study the reduced homological vanishing conjecture and compare the two cases. So that is our strategy. So any question about this outline? Okay, so let's first review the setup of KH local Picard groups and how this the GHMR detection map is defined and how like the vanishing conjecture plays a role in this computation. So the definition, the KH local Picard group, this was initially defined in the paper by Hopkins, Mahova, Sadovsky, and it is a Picard group of symmetric infinity, a symmetric monoidal category. I mean, it's an infinity category of the category of KH local spectrum, and where the smash product, where the tensor, the monoidal structure is given by KH localization of the usual smash product, and the unit is just a KH local sphere. And the first step in the detection is the first thing HMS they showed is the following. Since equivalent, one is X is an invertible KH local spectrum. And this is equivalent to, say, the molar module. If we forget about the group action, it's just an graded invertible EH star module. So this gives us the zeros detection map, which sends an invertible spectrum to its graded EH homology groups. And since EH is, we know the the molar E theory is even periodic. So this Picard group on the right-hand side is just sigma 2. So that's a zeros detection map. And we know this map is actually surjective because because S1 maps to the non-trivial element on the right-hand side. And from there, we can define the algebraic KH local Picard group. So first, let's define the pic naught to be the kernel of the zeros detection map. So that is the group of invertible KH local spectra whose EH homology are concentrated in even degrees. So basically the same as EH star. And for any such spectrum, the zeros EH homology comes with the GH action. That's because there's a relation between the group, actually it's not a group algebra, but it's the dual group algebra, and the EH star EH. So from there, we get the first detection map, which sends pic naught to the Picard group of GH, EH zero modules. So here it's not just the group homology, it's just the eCHT homology itself, but rather it comes with a GH action. And this is usually people call the eCHT, peak eCHT KH. And HMS, they show that there's a way to compute this peak eCHT. Basically, it is the first group homology of GH with coefficients in the units of pi naught of EH. So for example, at height 1, we can compute this very explicitly. At height 1, the action of GH is equal to the p-adic units, and the action, and then this units pi naught E1 cross is also the p-adic units, and the action is trivial. So this group now is just the continuous endomorphisms of the group of p-adic units, and we have two cases. And this is very easy to compute, since when p is greater than 2, the group is procyclic. When p is equal to 2, then basically the structure we can just use the structure of p-adic, the group of ZP cross, to compute this algebraic, even part of the algebraic K1 local Picard group. And now let's iterate this process. Now we have defined the first evaluation map, so we can define the exotic KH local Picard group to be the kernel of the first detection map. So how should we think about this? A homotopy groups of a KH local spectrum actually can be computed by a homotopy fixed point spectral sequence, whose E2 page are group cohomologies of GH acting on the molar module of X. Basically, that's the EH homology groups of X. And and so we have this spectral sequence. And so the E2 page, by assumption, the E2 page of the homotopy fixed point spectrums of any elements in these exotic Picard groups will be the same as that for the sphere. So to distinguish an exotic element from the KH local sphere, we need to look at higher differentials. And that's how Hopkins, Mahovan, and Stofsky show that theorem I mentioned at the beginning of my talk, namely the exotic KH local Picard group is 0 when p-1 does not divide h and 2p-1 is greater than h squared. Basically, what they showed is under this assumption, there's no differential on the E2 page, no higher differentials on the E2 page of the homotopy fixed point spectral sequence. So the question we are trying to answer is kappa h 0 when in the next case, that is when is kappa h 0 when 2p-1 is equal to h squared. So before we delve into the computation, well, I would like to show the proof. I would like to explain the proof of Hopkins, Mahovan, and Stofsky. So the proof of the theorem consists of 4 steps. Basically, it's an analysis of the E2 page of the homotopy fixed point spectral sequence. So it has several features. First, the zeroth line is constant for an exotic element. The zeroth line is concentrated just in the E00 term. In the E00 term, that's just a ZP, and otherwise it's 0. And then we have sparseness. Basically, the group homology is 0 unless 2 times p-1 divides t. And this implies like the first. Then if you draw the picture, then you'll say the first non-trivial differential in the homotopy fixed point spectral sequence is this d2p-1 differential. And then under our assumption, p-1 does not divide h. The cohomological dimension of sh is h squared. So this means we have a horizontal vanishing line. And if you combine all those results, then this tells you there's no room for higher differentials in the homotopy fixed point spectral sequence under our assumption. And once we have this, we can just pick, then that means any generator in the E00 term is a permanent cycle, and use that, and it converges to an element in pi naught of X, and use it. Then we can use it to build up a weak equivalence from the KH local sphere to X. So that is the strategy of their proof, and it's really an analysis of this E2 page of the homotopy fixed point spectral sequence, and under this assumption, there's no room for differential. Okay, so with that, so we have seen that in the proof, this d2p-1 differential plays an important role. So using this GHMR, they use this 2TP-1 differential to define an algebraic detection map for kappa H. And here's how they do it. So by assumption, since for an X in the exotic Picard group, we have this isomorphism, kind of a GH equivalent isomorphism. So let's just fix one. And then we can since it's an isomorphism, so induces isomorphisms on group cohomologies. So induces those two isomorphisms. And on the homotopy fixed point spectral sequence for X, we'll have a D2P-1 differential. That's the first non-trivial differential. And now we can just define this map phi. This induces a map phi X from between those two group cohomologies. And now we just set the second evaluation map, this detection map X, to be the image of the identity 1. There, it makes sense. There is some element, well, can be called 1 in this corner, in the upper left corner, since there's an element that can be called, since this is the zeros homotopy group of Lubin-Tate ring. There's a 1 here, and it's fixed by the GH action. And we can say the evaluation map of the second evaluation map for the exotic element to be the image of 1 under phi X. And of course, there's quite something to check. We need to check two things. The first is it's well defined, namely that this evaluation map does not depend on our choice of this isomorphism we started with. And second, we also need to check that this map is a group homomorphism. The group homomorphism part is basically identically boils down to the Leibniz, some Leibniz on the differentials. So by considering the higher and higher differentials in the homotopy fixed point spectral sequence, we actually get a exhaustive filtration on the exotic Picard group. So the zeros, so we just talk about the second evaluation map. And remember, we define kappa H to be the kernel of the first evaluation map. So we can repeat this process, and we define kappa H1 to be the kernel of evaluation 2, and then you check where is this next differential. So the target of the next differential will be on the E2P page, and it's of this term. And then we can iterate this process. At the end of the day, we get a kind of a filtration on the exotic Picard group, and it's detected by higher and higher pages, the terms on higher and higher pages of the homotopy fixed point spectral sequence. This filtration is necessarily exhaustive, because if an exotic element is in the kernel of all such algebraic detection maps, then that would mean there's no differential on the E2 page of the homotopy fixed point spectral sequence for that spectrum, and that means the identity element on the a generator of the E200 term will be a permanent cycle, and then we can repeat the proof of Hopkins-Sosovsky and show that element is, since it's permanent cycle, so it gives a wave equivalence from the sphere to this exotic element. So
yes.
Yes.
Can I ask a question? Aren't those higher? Don't you have cohomological dimension h squared, which is 2 to 1? So those higher, aren't those higher groups in the spectral sequence all trivial?
Yes, but that's under assumption when p-1 divides h. But this filtration works also without that assumption.
But you're assuming that 2p-1 is h squared. Right?
Yes, that's the assumption for our project. But for the more generally, if we just talk more generally about kappa h, then we'll have this.
So this is only going to be interesting if p-1 divides h.
Yeah, this should work for any p and h, this filtration.
Mm-hmm. But it's only. But anyway, it's only going to be really interesting if p-1 divides h, because otherwise most of those groups are going to be 0. And
actually, it's known that the homotopy fixed point spectral sequence will have horizontal vanishing line at EM page when n is large enough. Mm-hmm. So it's actually gonna be a finite filtration anyway.
Yeah. Okay.
Yeah. So the corollary we'll have is then this detection map will be injective when p minus 1 does not divide h and 4p minus 3 is greater than h squared. So that means this is because when under this assumption, the target of the third detection map, evaluation map, will be above the horizontal vanishing on the E2 page. So will be also above the horizontal vanishing on the E2P's page. So consequently, this means if the H2P minus 1 group homology, this group homology GH with coefficients in pi 2P minus 2 is 0. So that's the target of the evaluation 2 map is 0. Then this would imply kappa H is 0 under the same assumption. So this is our goal. So our goal will be, we'll try to compute this group homology under assumption 2p minus 1 is equal to h squared. And yeah, I guess now it also is a good time to mention another important component of our project, the chromatic vanishing conjecture. So the vanishing conjecture is proposed by Mark Hopkins, which says, which predicts that the inclusion map from the weight vector to the loop intake deformation ring. This is GH equivalent, so it induces maps on the group homology and group cohomology, and the vanishing conjecture predicts that this map is going to be an isomorphism on group homology and cohomology in all heights, primes, and degrees. And it has been proved in the following cases. When s equals 0 on the 0, when in degree 0, I should say this is for cohomology. S equals 0 for cohomology, I should say it's for cohomology. For homology, is unknown. So sorry, I should include this is for cohomology. Yeah, for I should say the conjecture has been proved in the following, the cohomology conjecture has been proved in the following cases. So s equals 0 when for all height and prime. When for height less than or equal to 2, when height is equal to 1, this is really a topology. Since the deformation pi naught of E1, that's the weight vector. That's just the p-adics. And height equals 2, it has been proved by many authors. So I apologize if I omit any citations. And yeah, so the case that's relevant to our project is the case we take the homological version of this conjecture, set s equals 0, so that's going to be the orbit. And we are going to mod out by p on both the weight vector and the loop intake deformation ring. So the reduced, so this is a special case of the chromatic vanishing conjecture, which says the inclusion map from this finite field into the mod p loop intake deformation ring induces an isomorphism in the orbits. And yeah, this computation, this part, like the H0 of GH with coefficient in this finite field, this is known to be FP. So basically, a little bit we want to show the right-hand side. So it suffices to show the right-hand side is just FP. So that's the reduced homological vanishing conjecture. I think at this step, I should probably mention like how to use this, the algebraic detection maps we mentioned before to compute some KH local Picard for H, for lower H. And I don't know if this is the state of the art now. So basically this was more or less extracted from the handbook chapter. So if anyone knows the update, please tell me. So at height 1, that's basically most of the computations were done in the paper by Hopkins, Mahov, and Sadovsky. So we know the evaluation 1 map, this is surjective, and their theorem implies it's 0 for odd, the exotic Picard group is 0 for odd primes. And when p is equal to 0, then the targeted evaluation map one computes explicitly, that's just sigma 2. So we have this result, this computation. When p is equal to 2, h is equal to 2 and p is equal to 3, then, sorry, when h is equal to 2 and p is greater than or equal to 3, then we have first, this evaluation map is surjective, which this is purely non-trivial. And then Hopkins computed the peak H0 for p is greater than 5, and this computation actually uses the vanishing conjecture at cohomological degree 1. And Karamanov showed this, the formula, Mark Hopkins formula still holds at p equals 3. And the theorem by Hopkins by Sadowski implies that the exotic group is 0 when P is at least 5. And then if P is equal to 3 GHMR, they use their detection. They show that the detection map is an isomorphism, and they computed this group cohomology, which is Zemos 3 cross Zemos 3. So in summary, we have these results for the K2 local Picard group when P for all primes. And I don't know, like, I don't know what the results at P equals to. So if anyone knows, yeah, I don't know what's the current status of ours at P equals to. Okay, so the next part of my talk. So now for the next part of the talk, we'll use duality to compute that group cohomology and try to reduce it. I don't know that you will say it's gonna be reduced to Greek element computations. So the first observation is for this Morat module M in top degree cohomology. So when P minus 1 does not equal H in top degree group cohomology, the group homology with coefficient M is isomorphic when the coefficient is M or P. So the more P reduction map induces isomorphism in top degree cohomology. And the proof uses basically we just look at this short sequence of Morat modules, and from there we get a long sequence of group cohomology. And then by considering the action of the center of the Morat stabilizer group, then this gives us a Linden-Hochschild spectral sequence, which tells you all those group cohomologies with coefficient pi2 p minus 2 of EH will be p-torsion. And then you plug it into the Lange sequence, then we can show that this is an isomorphism. So that's the first reduction. And then the second step is to use Poincaré duality. Since we are at top degree cohomology, and then this group SH under our assumption is a Poincaré duality group of cohomologic dimension p squared, so we can translate it back to H0. By H0, we can either mean zeroth group homology or zeroth group cohomology. So we now want to compute this group cohomology using in those two cases. So the T equals 0 case corresponds to the vanishing conjecture. The T equals 2p minus 2 case corresponds to the exotic Picard group. So the direct conclusion of HH squared is very intimidating and probably it's out of reach when H is greater than 3. So we use Poincaré duality to drag it back to H0. So this is the theorem of Lazard, and it's written in the book by Simons and Weijzhou. So SH is a PID Poincaré duality group of dimension H squared from there. This means that for any P complete SH representation, we have those two isomorphisms. For group, the duality between group cohomology and homology, we don't need to change the coefficients. The M is the same, but for the one between group cohomology, that connects group homology in degree S and degree S H squared minus S, and we need to take Poincaré duality. And so as a result, under our assumption, under this assumption P minus 1 does not divide H, the reduced homological vanishing conjecture is equivalent to the reduced cohomological vanishing conjecture in top degree cohomology. This is basically just follows from the Poincaré duality. And then there's next step is to use Gross-Hopkins duality to identify the punctuation dual of M. And so the identification is let M, this mass frac M, be the maximum ideal of the Lubin-Tate deformation ring. Then the punctuation dual pi t, the equivalent punctuation dual of pi t of EH is given by this formula, where this that denotes the determinant twist of the stabilizer group action. And mod M, and then on this side we'll have mod M infinity. So the next thing to do is to understand the determinant action. But we're actually, there are two ways now to compute this group homology in this fixed points. One is to incorporate the determinant action determinant twist. Or alternatively, we can identify the determinant twist mod P. So far we have shown this isomorphism. So we have connected the top degree cohomology to pi0 of this twisted Moral module and mod P. It's complicated. So next step is identify the determinant twist mod P, and across Hopkins, they show there's an isomorphism of GH modules, where the right-hand side here, we have a limit in the suspension, which is pretty intimidating. So what this really means, there are two ways to think about this limit. One is to say it's actually, this limit really happens in the Picard group. This limit really happens in the Picard group. The Picard group has a p-adic topology, and this limit happens in the Picard group. Another way, more precisely, another way is to say, let J be an open invariant ideal of the Lubin-Tate deformation ring containing P, such that the quotient has VH to the P to the N self map. Then in that case, if we modify by J instead of by P, then this becomes a finite suspension. I mean, the reason it reduces to the finite suspension is like, once you modify by J, the quotient moral module will have a periodicity map. That's our assumption. And then we can drag the suspension back to homotopy, the index of homotopy groups. So now we want to compute the fixed point of the quotient group. Sorry, wait a second. And so let M be a moral module. Recall that by mod P plus H infinity, we really mean a colimit of quotients, where this J, this ideal, ranges over all open invariant ideals of AH containing P. And this colimit is filtered. And notice this colimit is filtered, and the small moral stabilizer group is topologically finitely generated. So that means the canonical map, when we take the colimit of fixed points, that's going to be isomorphic to the fixed points of the colimit. So consequently, in this section, we have established this isomorphism where the left-hand side is the group we want to compute. Is a group which we want to compute. The right-hand side is the fixed points, the colimit of fixed points after we use the reduction by duality. So, and where this nj here, this index is the smallest n, such that it's basically the period of J, sort of the quotient of pi naught EH by J. So our goal for the vanishing of the Picard, exotic Picard group is to show the left-hand side is 0 when t is equal to 2p minus 2. We want to show that by showing every single term in the colimit on the right-hand side is 0. And for the vanishing conjecture, that is when, so the vanishing conjecture should take t equals 0, and we want to show the left-hand side is fp. So we'll show that by showing every single term on the right-hand side is fp. So now you can say sort of Greek letters are going to show up. And that brings us to the last section, where it's a real hard computation, Greek letter elements. But before the hard computation, the first step is there's still one step transition from Morava modules from the Lubin-Tate ring to BP. So that's the Morava's changeable ring theorem, which states there's an identification between the group homology of GH with coefficients in pi t EH mod M infinity and the X groups, BP star BP X groups. So here when BP star BP, so left-hand side is the KH local sort of, it's at height H. So the right-hand side, we are inverting VH and then taking the IH infinity, where IH is this invariant prime ideal of BP star. So now that J be an invariant ideal of BP star such that it contains P and containing in IH, and then let M be the smallest number such that VH to P to N is invariant mod J. So under the changeable ring theorem, so our computational goal is the following. We want to show this group homology. So we want to show this BP star BP X group is FP when T is equal to 0, and is 0 when T is 2P minus 2. The first case corresponds to the vanishing conjecture. The second case corresponds to the vanishing of the exotic Picard group. So let me remind you of some classic computations of Greek letter elements. So let M up K lower H minus K to be this module, BP star BP co-module, where we invert VH and then quotient out by P V1 VH minus 1, and then we K infinity all the way up to V n infinity. This should be an H. Sorry, this should be an H. This then should be an H. And then back in the 70s, Miller Wilson did this computation where they computed the fixed point, the zeroth line on the zeroth BP star BP X group of M upper H upper 1 lower H minus 1. So they gave up additive basis of those X groups. So it consists of the following three families. The first family, where you'll see the degree of the denominator are all 1. That's the first family. In the second family, the numerator is 1. And then the denominator for the first P from P V1 all the way to VH minus 1, the degree is 1. That's because we are quotienting out by P V1 up to VH minus 2 in this module. And then there's no constraints on the power of J here, on the power of H minus 1. And then the most complicated family is family 3, where the numerator is no longer, numerator is some replacement of VH to the P to the N. And then for the denominator, the bounds on the divisibility of VH minus 1 is given by some recursive formula. So I'm not going to write down the recursive formula here. So this means for an invariant ideal that's sandwiched in between IH minus 1 and IH, this H0, the zeroth X group, is then generated by the elements above, such that this ideal J is contained in the ideal generated by the denominator of those elements. So now using this translation between zeros between BP star BP X group to group homology, and then duality to top degree group homology, then we at least get some identification. Oh, sorry, this side should be more normal P, probably it's normal P. Yeah, so the number here, if we trace through the degree, then alpha, this element in M upper H lower H minus 1 corresponds to elements in top degree group homology, if I know, and here it's pi T in homological degree T, if and only if the degree of alpha is congruent to this formula, more P to the N times VH, times the degree of VH. And then this means in this computation, yeah, sorry, so in this line, this here it should not be more P, it should be more this ideal. So this now the Miller-Wilson's computation now implies the top degree cohomology of GH pi T EH modulo this ideal is 0 unless two cases. Family 1 contributes to the element, will contribute elements where the degree T, this homological internal degree T, is divisible by the degree of VH. And then family 3 will tell you T, in other cases when T is equal to this formula for some n greater than 0 and J between 1 and the bounds in the Miller-Wilson computation. So this actually, when at H equals 2 and P greater than 5, we actually recovers the computation of Mark Behrens' computation of the top degree group cohomology of G2. So at when H is equal to 2, we are only quotienting out by P. So when H is equal to 2, there's the ideal equation is just P. So you have different families. So this is a picture from Mark's paper. And this is the part I would like to annotate. But okay, can everyone say that the picture has been zoomed in? Can
yeah,
I see
I
that?
can see that. Yeah.
Yeah, so this picture, basically, this is the first case. And I think this is degree 0, 1, 2, 3, and 4. So we'll say there will be one element when there will be a dot, an element, when degree of V2 divides T. So that corresponds to family 1. And then in other families, so there in this second picture, this dot corresponds to family 1 element, and this corresponds to V1 family. So the tail here is SP minus 1, V2 SP minus 1. If we go back a page, can I go back a page? Oh, no, what's happening? If we go back a page, and then if we plug in J equals 1, so this term is gone. And in that case, N is equal to 1. So this term is just the degree of V2, and that's just SP minus 1 times V2, and that's precisely the degree. Wait a sec, sorry. I guess it's, okay, sorry about this. Then we can say in the picture here, the tail of this divisible family, that's precisely the degree of V2 to the SP minus 1. That's when J is equal to 1. And when it reaches the maximal divisibility, it's something somewhere here given by the recursive formula. And similarly, if you look at the next picture, this is the family 1 element. This is the element we saw before. That's the V2 to the piece power. And yeah, it's V2 to the SP square minus 1. So it's the same as the previous case. But now we have another family. And in this case, the tail is, we need to subtract minus P minus 1. So basically, we can recover the pattern on the top 9 of in Mark's paper. And moreover, and also one thing to notice here is, so I guess in the zero span, when we say the V1 divisible family, like the V1 tower goes towards left, so you divide V1, so we lower the degree, lower the internal degree. But when you do duality to flip it back to the top degree cohomology, when you do this tower, it's gonna increase the internal degree because of the duality. That's gonna be important later when we show the implication of the Greek letter of the vanishing, when we show that the vanishing conjecture implies the vanishing of kappa H in one case. Okay, so what's the implication? The implication is, so when P minus 1 does not divide H, the above computation yields. So first, the 0th degree homology, when we quotient by IH minus 1, this is isomorphic to the top degree cohomology, which is equal to FP. Of course, the second map, this is not that canonical because we're taking punctuation dual. So, I mean, it's a finite group, so punctuation dual is an non-canonical isomorphism. And then it also tells us H, when we do the 0th group homology with coefficient pi 2p minus 2, and again, modeled by H minus 1, we get 0. And then when 2p minus 1 is equal to H squared, this group homology measures whether unexotic elements in kappa H are detected by smashing with, detected by the Smith-Stoddard complex. So this is related to the, basically related to the topology on kappa H. It's like on pi, yeah, this is related to topology on kappa, which I think is explained in the survey paper by Gors and Hopkins. That's, I think it's, they posted last November. Yeah, and wait a sec, it's just, probably it's H minus 2, I apologize, H minus 2. Should be V of H minus 2, sorry, I apologize for the typo. So from this, we conclude that the Smith-Stoddard when the Smith-Stoddard complex VH minus 3 exists and 2 minus equal to H squared, then an exotic element cannot be detected by the Smith-Stoddard complex. And in particular, we know the Smith-Stoddard complex VH minus V1 exists for P equals 3 and V3 exists for P equals 13. So we know at least for kappa 3, exotic elements in the Picard in height 3.5, exotic elements cannot be detected by V of 1. And similarly, at height 5, point 13, exotic elements cannot be detected by wheel of 3. And I think I'm running out of time, right?
Right. The talk is 45 minutes.
Okay, let me just state the final theorem. So more generally, there also have a similar. So even though we cannot compute all the Greek letter families, we can still get some classification of their families, and then from there we can get some bounds on the ideals, on the divisibility of the Greek letters that would imply the vanishing conjecture and the vanishing of the exotic Picard group. So the bounds are pretty closely related to each other. It's just the bounds for the vanishing conjecture is stricter than the bounds for the vanishing of the exotic Picard group. So, but the direct implication is probably not possible, but nevertheless, at height 3.5, we do have an implication. And that uses our previous computation, that uses the Miller-Nelson computation. So basically, the idea is we'll prove this. We can prove this by a sort of a contrapositive argument. Say if there is an exotic element, and then there will be an element in top degree cohomology, and that element is not necessarily cannot be V1 torsion, because first we show if we multiply both 5 and U1, the group home is 0. So we can just multiply that element by V1, it's non-zero. And then if you flip it back to the top degree cohomology, then that lowers the internal degree by the degree of V1, which is precisely the subject of the vanishing conjecture. So basically, by that we mean if kappa 3 is not 0, then this group homology definitely will have at least 2 copies of FP, so the vanishing conjecture will fail. So that proves the implication. And sorry for running over time, and sorry for the typos. Thanks for your attention.
Let's thank Ningchuan.